All right. Well, thank you, Dan. Thank you very much for the invitation. Yeah, I thought I'd kind of talk a little here about my take on where things are with the Hubble tension. So I'm going to frame things around these three questions. What is the Hubble tension? Why hasn't it gone away? What should we do about it? And hopefully offer a couple of comments on some lessons I think we can learn from this more broadly in research and cosmology. So I tried to come up with a one sentence summary of the Hubble tension. It's a bit tricky because you need to fit lots of words in, and this is still a bit of a simplification, but I gave it a shot. So the Hubble tension is the disagreement between H0 values inferred within the standard lambda CDM cosmological model from observations of the early universe and more direct low redshift measurements. So there's definitely some caveats and extra details there that I'll talk about. But more or less, the way I think about this is with this divide between measurements like the cosmic microwave background, baryon acoustic oscillations that are sensitive to physics of the early universe, that are sensitive to our assumptions about the cosmological model, lambda CDM model, versus some more direct measurements which are more empirical, which are not based on fundamental physics, and more direct probes of the expansion history at low redshift. So I wanted to start by showing a few slides from Adam Rees. Adam is the leader of the SHOES team. SHOES stands for supernovae H0 for the dark energy equation of state. And his team has really been making these ever more precise distance ladder measurements using this distance ladder approach. So these are some slides that Adam presented recently at a conference in Tehran. So what's the distance ladder? How does this work? Why is there a ladder? A question I cannot answer is why it comes in serving sizes of one potato. So we'll move on from that. But right, essentially, the problem with measuring the Hubble constant directly is we don't have enough volume actually at redshift 0, particularly, to get reliable distance indicators. So type 1a supernovae are each good to something like 6% in distance. This is based on empirical relations between the peak supernova magnitude and light curve and its intrinsic luminosity. But unfortunately, type 1a supernovae don't go off in the local, very local universe frequently enough to be able to just directly measure distances to the supernovae. So that's where this ladder comes in. So it's the supernovae out in the Hubble flow out to redshift 0.1 or 0.15. They're actually used to trace out the distance redshift relation and sort of back out H0 from working down to redshift 0. But to calibrate the absolute magnitude of the supernovae, we need another kind of standard candle or standardizable candle. And that's where these Cepheid variable stars come in. So Cepheids are common in spiral galaxies, including the Milky Way. And unfortunately, they're not quite bright enough to be seen out into the Hubble flow. There's some prospects for a Cepheid-only ladder, if you like, in the future. But right now, what's done is the Cepheids are used to calibrate the absolute magnitude of the supernovae, and then the nearby Cepheids, the first rung of the ladder, can have direct distances calibrated with parallax, for example, in the Milky Way. And I want to emphasize here, again, this is an empirical ladder. So certainly there's interesting fundamental physics that goes into supernova explosions, but the relationships that are used, the period luminosity relation for the Cepheids, the light curve relation for the supernovae, those are all empirical. And there's very little in the way of model assumptions that are going into the ladder. So the state of the art in terms of the results, as of a few weeks ago, in this new paper by Rees et al. From 2021, is achieving this precision of about 1.8%. And so there's the three steps of the ladder sort of shown schematically here. So distance is increasing, going off to the left. So here are Cepheids in the Milky Way or nearby galaxies where the distances can be measured directly, for example, using parallax or other methods. Then in the middle here, we've got galaxies that have both a type 1a supernova and a population of Cepheids that can be studied. So that's where the absolute magnitude of the supernovae get calibrated. And then in the third rung, there's all these supernovae, and there's larger samples than this, of course, going out to higher redshift. But there's all these supernovae out in the Hubble flow that are then used to trace out the relationship between distance and redshift and infer H0 with minimal dependence on things like, what the equation of state of dark energy is, or on other cosmological parameters. Okay, and I want to sort of shout out the SHOES team, I guess, for doing, I think, a very impressive job with self-consistency checks and redundancy in this ladder. Because it's an empirical ladder, one has to constantly check the assumptions, check that the parameterizations of the period luminosity relation or the supernova light curve relations, check that those are actually sufficient, those are actually fitting the data. And the modern distance ladder has a lot of inbuilt redundancy to basically try to minimize the chance of a sort of a single point of failure, which could mess up the whole ladder. So here on this slide, there's several, as an example, there's several absolute distance measurements. So here there's Milky Way parallaxes directly to Cepheids, updated with the new Gaia data release 3. There's an absolute measurement that's independent of parallax that goes to this galaxy NGC 4258, which has a water maser, and one can actually infer more or less from the Keplerian orbits of the masers, the geometry, and infer a precise distance there too. And then there's another method using orbits of detached eclipsing binary stars that's independent from these other two. And so you can calibrate, you can anchor the whole ladder from these three separate base points, if you like, and check that you get consistent results. So, this is the sort of progress in the last few years that has really, in my mind, made me sit up and pay more attention to these distance ladder results. I certainly think this is all a very far cry from the historical distance ladder, which, they didn't have HST, which is a big deal, but also this level of redundancy was never available earlier. And then there's just at the bottom here, there's some extra checks for absolute distance calibration too. Another observation, I guess, I want to make about the distance ladder is, of course, this tension's attracted a lot of interest. And because the SHOES team have made varying levels of data products publicly available, a lot of teams have independently been able to go and reproduce part or pieces of their analysis. So I just have a sample here of papers you can see from the last few years that are going in and doing the statistics differently, or going in and switching out some assumptions about the Cepheids, or using observations in the near infrared, on the supernova side rather than in the optical. And I think this is absolutely fantastic. This has been possible. And again, I give credit to Adam and colleagues for increasingly making an effort to make the data public. There's this one paper very recently where a team mostly based out of Paris, I think, went back to the HST photometry and really did from scratch a lot of the process needed to get the all the period luminosity information on the Cepheids out, and got very consistent results with SHOES. So I think this is great, and another reason why I don't really see at the moment a compelling reason to ignore this measurement. I will say, I do want to comment on this paper by George Evstathiou. So he had a lot of criticism in this paper, a lot of issues or potential issues that he raised. And there's a very nice discourse actually between George and the SHOES team in the text, if you're interested in going to read that. And a comment I wanted to make here is that a lot of George's criticisms were about some earlier versions of the data that have more or less been shored up now. And particularly, he was concerned about some of the distance anchors, and the new Gaia data more or less has come in and, in the table I was just showing, given very consistent results with the other SHOES calibrators. Okay, so that's the sort of latest status here on the Cepheid distance ladder. Of course, there's a lot of other techniques that people use to measure H0 at low redshift. So this is a plot, or half a plot, to be honest, that I took from this recent review paper. So here you can see this red band is the Planck uncertainty in lambda CDM, and then these different categories of types of observations. So the Cepheids and supernovae, including some, lots of these points are basically using data from shoes. But there's all these different techniques that have come up as well. I say come up, some of these have been around for decades, but the recent, highlighting of the Hubble tension has pushed a lot of teams to go back and bring out new numbers, reanalyze, and so on. So, generally speaking, you see this preference for higher values. You have to be careful with this plot because, of course, each set of points have a lot of correlations. But there is support from other partially or fully independent data sets for the shoes values. I wanted to add this last, possibly provocative, but I think important comment here, which is I do worry a little looking at this. Are all the values getting written up and published? So it's certainly true that you don't see points down here that have sort of scattered down, 63 plus or minus 3 or some number like that. But this is clearly a case where there's sort of one would have a preconceived bias or notion of what the true value, correct value should be. And I do worry a little about what role that could be playing. All right, so I do want to talk briefly about a couple of specific other data sets here. So firstly, the tip of the red giant branch. So this is an alternative calibrator to Cepheids. And Wendy Friedman, who led the Hubble Key project and is an expert on the distance ladder with many decades of experience thinking about Cepheids and these other stars as distance indicators. So she's moved away from the Cepheids and focused on this different distance indicator. So the way that this works is instead of measuring individual Cepheids, measuring their periods, you measure this whole population of stars that are undergoing the onset of core helium burning. So the idea is that this is sort of a standardizable explosion, almost, if you like, or bright discontinuity in the red giant branch luminosity function. And particularly in the I band, it's a pretty good standardizable candle. So you measure populations of these stars, and these are ubiquitous in basically any nearby galaxy, whereas the Cepheids are only found in the spirals, not ellipticals. So there's various advantages like this. And I think, Wendy would argue one issue on the shoes team is pushing the HST photometry maybe a bit too hard in these faint distant galaxies where there's a lot of blending of different stars. And this alternative approach gets around some of those issues. So here's the curve or the plot from Wendy's paper from a year or two ago, and her constraint is sort of tantalizingly in the middle here. I want to just mention briefly that there is a bit of an issue with the TRGB calibration that is not, to my understanding, fully resolved yet. So it doesn't have a counterpart on the Cepheid side, but when you're trying to get basically get the first rung of the ladder working for the TRGB stars, there is this question about reddening and extinction corrections. So if I just come back to this previous plot, you can see that these pink bars, which are from the same technique using the TRGB, then the supernovae, there is this scatter. So there are some of these analyses that get values centered more at 71 up towards 72, whereas Wendy's team is more like down at 70. And the main reason for that is this extinction correction. So there's a lot of recent literature about this. It's sort of the main systematic, I think people would agree, that needs to be sorted out here. My understanding is there's good prospects for more information on that coming up, but that's sort of there is the systematic reason for why there is a bit of an offset here. It's not purely statistical. Okay, so changing gears a little and talking about a different method that's completely independent of the supernovae, but has really been very promising the last few years. are using strong gravitational lensing time delays to infer H0. So the idea here is you have a lensing system with these beautiful lensed images, and provided the background source is variable, so for example, some kind of variable quasar, you can actually measure that time variability in the different images with a time lag, time delay coming from basically the different light travel times corresponding to those images. So you need a lot of things to kind of go right to have these systems, and they're very rare. But if you can make those time delay measurements, and if you can do a good enough job of actually modeling the lens, the lens potential essentially, you can back out a distance, and that's, that ends up being very sensitive to H0. So I'm showing a plot here from the Holy Cow team. They used 6 lenses in this analysis, and they used this technique. And in this result, they got out a result of 73.3 plus minus 1.8. This is completely independent of the distance ladder. There's no Cepheids, no supernovae involved here. It's a little bit more cosmology dependent because these quasars are not at a very low redshift. They might be at redshift 0.5 or redshift 1, but it happens that effectively the distance you measure is actually pretty robust against modifications in cosmology. So this was a really exciting result, and a lot of people, sat up and paid attention to this. A lot of people also criticized it. And so I wanted to tell a little more about the subsequent history here, because I think this is something certainly, say, my colleagues from the CMB side somewhat misunderstood. So after getting that result and seeing the implications, the experts on these lenses, so originally it was the Holy Cow team, and then they sort of merged to form this new TD Cosmo team. They were very concerned about this mass sheet transform degeneracy, which is a degeneracy where essentially you can trade off H0 more or less directly with the assumed profile of the lens. So in the original analyses had these smaller errors. They're making assumptions about how the stars and the dark matter are distributed in the lens galaxies. And they wanted to back off that, and they deliberately chose new modeling, more essentially throwing out information, what we thought we understood about these elliptical galaxies, and did this modeling in such a way as to be maximally degenerate with H0. And, so you can kind of see, you go from this error bar to getting an error bar several times larger that's just from this, this different, relaxing the assumption. And then there's sort of a secondary issue with these points down here, where adding a second population of lenses then shifts the results, although the error bars are large enough that the shift isn't particularly significant. But as I was saying, I think colleagues of mine looked at this result and had the view that, okay, they start out with a small error bar, they went back to the analysis, they found something that was wrong, they realized the error bar should be a lot bigger, and that's here, here we are now. And that's not quite the impression I get from the paper or from talking to the TD Cosmo folks. These error bars should really be interpreted as an upper limit, a worst case. And there's no actual direct evidence that the modeling done here was insufficient. So there's still a big question here, of course. It definitely underlines the importance of this, this mass modeling. And my understanding is there'll be hopefully new results by the end of the year to try to bring in more kinematics information and bring these error bars back down again. And it'll be very interesting to see what happens with that. Okay, but I wanted to make this point that these newer, larger error bars do not invalidate the original results. It's a different set of assumptions, but there's no direct evidence that the old assumptions were actually wrong. Okay, so I've talked about a few of these low redshift data sets. I want to switch gears, talk about Planck and constraints from the early universe. So of course, the bottom line from Planck, as I'm sure you're aware, is we find no compelling evidence for extensions to the base lambda CDM model. So Planck really sharpened the precision on the CMB side in determining cosmological parameters, both within lambda CDM and then testing many viable or well-motivated extensions. And thanks to the beautiful Planck data, there's this very precise constraint on the Hubble constant within lambda CDM. And I wanted to make the point as well that there's enough redundancy within Planck that you don't actually have to use this sort of iconic power spectrum data, the temperature power spectrum. If you actually just use the Planck, the cross spectrum between the temperature and the E-mode polarization, so none of these data points at all being used in this right-hand value, you still get a precise value that's uncomfortably low compared to the distance ladder. And this plot up here is showing how the polarization and temperature data break degeneracies within the lambda CDM parameters. So there is this great valuable cross-check on the polarization. So when I moved to Johns Hopkins, one thing I was really interested in back in 2015 or so was this idea of consistency between WMAP and Planck. So is Planck seeing the same thing as WMAP over the range of angular scales where both had lots of signal to noise and you can do the comparison? And this is a really key question that I worked on with a graduate student, Yajing Huang. And we basically went back and estimated the covariance between the power spectra coming out of WMAP and the power spectra coming out of Planck. This is our estimate over here. So there's 3 lines because Planck used different sky masks for different frequencies. So you can see that the 100 gigahertz mask had a larger area of the sky that was most similar to WMAP. And that's why this correlation in the blue is the largest. And this fall off with multipole is essentially reflecting the fact that the WMAP data gets noisy on smaller angular scales. But you can see that you have a very stringent test of consistency here because the error bars on these scales in both experiments are dominated by cosmic variance. So you really should be seeing the same thing, and that lets you do a more powerful consistency test than you could with just a single experiment. So Yajing went through simulations for this, and we ended up with this plot here, which is more or less showing binned power spectra differences normalized such that every error bar is size unity. And we stared at this and we thought we saw some slightly funny patterns. And so we did some tests for the funny patterns. And we quote some other numbers in the paper. But the bottom line is that the WMAP and Planck 2015, and also I should say 2018 subsequent data too, are actually in good agreement. So our final number is within 1 sigma. There's no real statistical evidence for differences here. And this is great. I mean, I don't want to undersell this result. It's absolutely critical that we do these sorts of checks, particularly with 2 data sets where you do have this opportunity to really do a very precise comparison. So what about the additional information at high multipoles that WMAP wasn't able to measure? And that's where things get a little more interesting. So on this slide, I have presented 3 what I'm calling curious Planck symptoms. So these are effects that are essentially deviations, if you like, from the standard lambda CDM assumptions at low significance, 2.5 or 3 sigma, that are nevertheless perhaps worth thinking about. So the first one, this is something I looked at again with Yajing back in 2016. There are shifts in parameters, some parameters in particular, with multipole. So the red points here are L less than 1,000, more or less the range accessible to WMAP. The blue points are L greater than 1,000, so that new information coming from Planck. And for sigma 8, roughly the clumpiness of matter in the modern day universe, omega m, the fractional matter density, and h naught, these are all correlated parameters, I should say, so you don't get to sort of triple count these. But nevertheless, you can see there's this offset such that, the L less than 1,000 data or WMAP is consistent with h naught closer to 70, whereas lower values are preferred by the higher multipoles. And at the time, there was a bit of uncertainty about the optical depth to reionization. So we did this analysis for different values of this tau parameter, but it doesn't make too much difference. And in fact, if anything, these differences are a bit larger for the low values of tau that the newer Planck polarization data is favoring. Okay, so 2 related symptoms, or I guess you could say ways to alleviate this difference. Of course, in lambda CDM, you don't get to have 2 sets of parameters, one for each half of your data. But you can imagine introducing additional parameters that absorb some of this difference, and that's exactly what's shown here. So one way of looking at that is through this AL lensing amplitude parameter. So this just dials up or down the amount of lensing that goes into the basically the peak smoothing of the CMB power spectra. And so you get this preference, you can see in the blue or in the black, from the Planck temperature and polarization data for roughly a 3 sigma, 2.5, 3 sigma preference for this in excess above the fiducial expected physical value of 1. So this is another manifestation of the same effect over here. And similarly, if you open up global curvature, so omega k is a free parameter rather than assuming flatness, you similarly find that the Planck contour pulls away, the Planck temperature and polarization data pull away from flatness with a significance of roughly 3 sigma. And other data sets like there's, the BAO that I'll mention in a few minutes are shown up here. Those are more consistent with flat. And so there is just this discrepancy. And a number of papers have discussed this point. So it's not clear to me what any of this has to do with the Hubble constant tension. Certainly no one's managed to make a model, a physical model, to explain these effects. We do know that it's not really excess physical lensing. And we also know it's not really non-zero curvature because there's other data sets that rule out those possibilities. So, and I'm sorry for the confusing wording here, but lensing here refers to a reconstruction from the non-Gaussian statistics of the CMB maps of the lensing potential from Planck itself. So there's this internal tension between the lensing effect that's moving the peaks of the power spectra and the lensing effect reconstructed from the non-Gaussian statistics. And I mentioned, as I mentioned, there's other data sets that rule out these values of omega k that Planck on its own is preferring. So I wanted to put this up because it maybe it relates to the Hubble tension. I think it's still quite unclear. These effects have not been reproduced yet in other CMB data sets. That's partly a statement about lack of precision. We don't have data with Planck's precision at high L in the TT data yet, for example. But it's still an intriguing puzzle that may yet come back in the future or be telling us something interesting. Okay, and just before I wrap up talking about data here, I do want to bring in the Baryon acoustic oscillations as an extra probe sensitive to the physics of the early universe that plays a really important and I think somewhat underappreciated role in all this. So what is the BAO scale? It's basically how far sound waves can propagate in the plasma of the early universe prior to photons and baryons decoupling. And the distance that the sound waves can propagate is imprinted thereafter, both in the photon distribution CMB, but also in large-scale structure. So when subsequent, nonlinear collapse and formation of galaxies and so on takes place, this so-called standard ruler scale is imprinted and then measurable in the later universe. And a key thing here is that this scale is long enough, about 150 megaparsecs, that it's roughly unchanged by nonlinear growth. And that's why trying to measure this scale in different surveys in large-scale structure is really powerful, because you have a pretty linear probe that you can directly couple back to the physics, the understood physics, understood at a fundamental level, to do with recombination. And so this key quantity is the sound horizon, which is this integral, basically, of the sound speed over the expansion rate in the early universe up until this drag epoch. And I've worked on cosmology from the BAO scale for a while. I think to me, the most impactful single experiment has been BOSS from one of the SDSS surveys. So this is an enormous spectroscopic survey, 1.4 million galaxies. You can see a lot of them are at redshift 0.5 or so. And the cosmology observable they're going after here is the BAO feature in the correlation function. So that's shown in this peak down here, or these wiggles in the power spectra. And BOSS really, I think, took the BAO measurements forward in precision. And there's a whole set of future experiments that are aiming to sharpen this precision even more and go over a wider range of redshifts. I also want to mention last year, the EBOS collaboration came out with their sort of final results, which then, of course, improved further on some of these measurements as well. In terms of H0, a point I really want to make here is that the BAO scale measurements alone do not constrain H0. So if you don't know how long the standard ruler is, there's this complete degeneracy between the ruler length RD and the overall expansion of the overall normalization of the expansion history, which is the role H0 performs. But you can still end up with a precise constraint on H0 from the BAO without bringing in CMB anisotropy data, so no data from Planck. And the way this is done is using estimates of the primordial deuterium abundance and BBN physics. And that essentially lets you calculate the sound speed and the Z drag you need to actually evaluate this integral. So this is a very powerful way to get an H0 that's independent of Planck. It does assume lambda CDM, so that need to make that clear. But by combining BAO measurements at high redshift, so from the Lyman alpha forest, with the galaxy BAO at lower redshift, you do get this precise constraint on both the matter density and on H0 with this process. So here is the latest constraint from EBOS, 67, 0.35 plus or minus 0.97. And so even though individually the Lyman alpha and galaxy BAO tolerate these higher values of H0, there's no way that they agree on the matter density except down in this lower range. So this is important, right? Because this has nothing to do with Planck. It does assume the standard model, but it's a completely independent set of observations, and it's coming out low. I want to just mention as well that the precision of this has really advanced a lot, because when I originally came up with this idea and worked on it with the BAO available at the time, I got an error bar that was over 3 times larger than what we have now, and that was 7 years ago. So this is again testament to BOSS and other surveys for the advances that they've made there. Right. So kind of drawing together constraints from the early universe, the CMB, the BAO. I made this quick summary slide. It's just a 1D slice looking at H0. These blue points are all different CMB measurements. So at the top here, I've got 3 experiments that made measurements independently of Planck. As I mentioned, a lot of the information in WMAP, more or less all the information in WMAP was in Planck too, but it's still an independent, the observations were taken independently. And then there's 2 ground-based surveys here, SPT-pol and ACPOL, that have three or more, factor of 3 or more better angular resolution than Planck, but looking at smaller areas of the sky, so hundreds or a few thousand square degrees. ACT is actually now scanning close to 20,000 square degrees. And then here I've got the Planck points, and I included this split in multipole from the temperature power spectrum that I mentioned. So you can see there is some scatter in these points. Certainly SPT-pol and ACPOL don't quite have the precision of Planck, mostly just because of the sky area. And there is, again, highlighting this difference between the high and low multipoles on the Planck side. This is Planck throwing everything in together. And then this is this Planck independent or even CMB anisotropy independent constraint I just showed on the last slide. And just as a point of comparison down here is the distance ladder. So all these points assume lambda CDM. And I wanted to also just illustrate here the synergy between the CMB and BAO measurements. So all the blue points here now have a green counterpart, which comes from adding in the BAO data, mostly from BOSS, but other surveys are all being thrown in there too. So you can see in the case of SPT and ACT, the error bars come down by about a factor of 3. The BAO are just incredibly effective at breaking degeneracies in the CMB data. So the conclusion here, right, is that you have these green points that are very narrowly scattered down at this sort of 68 value. And all this really is to say, I think that on the early universe side, there's no single experiment that's driving this preference for the low value. You can take Planck out completely, and other CMB experiments plus BAO still have the preference for low values. You can take the CMB anisotropy out together, altogether, and then you still have this point that's in tension with the distance ladder. So this is not a Planck tension. Right. So let me move along here and get on to talking about some other things. So why hasn't it gone away? Why, why are we still talking about this tension? So I've addressed this slightly. I've talked about lots of different sort of consistency and redundancy across different observation types. I want to turn, take the tension at face value, turn to theoretical explanations. And I want to also shout out this quite nice paper trying to walk through challenges of coming up with theoretical solutions by Lloyd Knox and Marius Millier. So separately from the Hubble constant tension right now, there's this $1 billion observational program underway to try and understand dark energy. I threw up a few of the current stage 3 weak lensing surveys here just because I'm not talking too much about weak lensing, so it's nice to have them up on the slide. And then future surveys I'm sure you're familiar with in the near term. So, it'd be really nice if this tension on the Hubble constant side was kind of pointing us to needing to understand dark energy better. And we have this fantastic suite of experiments, coming online this decade that can really help pin that down. Unfortunately, it doesn't seem to be so simple. And efforts to try and explain the Hubble tension using modifications to the late time expansion, modifications to how dark energy works, have not been particularly successful. The bottom line is just that there are too many data sets that are too constraining. And it's this combination, it's CMB, BAO, and the supernovae. So that I'm not talking about the distance ladder here, but the supernovae over a whole wider redshift range. They just really strongly constrain deviations away from the lambda CDM expansion. So this is a kind of an amazing plot showing H naught in the matter density, lambda CDM, so CMB, BAO, supernovae. So lambda CDM is in the blue, and then allowing curvature W naught and WA to various sweep parameters gives the red. And this isn't, some kind of Fisher forecast. This is the data, right? You blow up the error bars somewhat, but you really don't shift the constraint. And of course, people have done a lot of work with more flexible dark energy models, not just W naught and WA, to try to push on this and see, is there some mileage for relieving the H naught tension without messing up other data? That's the key thing here. So this plot is showing you've got the BAO measurements both in the basically transverse on the sky along the line of sight, and then supernovae binned up here by redshift. The exact values of the parameters from these other models, so W, open, and a model with massive neutrinos aren't too important. The point is that you have essentially enough of a lever arm in redshift and enough precision from these measurements that you really strongly constrain these deviations. So the prevailing thinking, I would say, there have been a number of recent papers on this, is that it's very hard to modify the expansion history at late times and solve the Hubble tension without introducing new tension in some other measurements. So there's this approach called the inverse distance ladder, where you don't make an assumption about the exact form of the expansion history. You use some kind of Gaussian process regression or some cubic splines or some more sort of model independent method, and you fit the supernovae and you fit the BAO using the sound horizon from the CMB. And so that's the exercise shown in these panels. And essentially the point is that, as far as people can tell, it doesn't matter how you do that parameterization, you really struggle to get up to 73 at redshift, as redshift goes to 0. And this plot over here is just visualization of just the number of supernovae and the redshift range they cover, just to give a sense of how well the distance redshift relation is traced out. Right. So what about changing physics in the early universe? So one attractive idea that came up a couple of years ago is this early dark energy. And I found this nice plot by Katie Fries in a recent paper. So the idea here is there's an extra scalar field. It doesn't couple electromagnetically, and it doesn't behave like radiation or matter or lambda, but it's this, it makes a contribution to the energy density here, so just before recombination, then rapidly decays away. And the idea is to modify that sound horizon calculation. So you get to shift the sound horizon from the CMB and BAO and essentially change the early universe prediction for H0 that way. Unfortunately, it's tough to get this to work because, of course, one has to treat not only the background expansion, but also perturbation self-consistently. So the issues with these models, so far at least, seem to be that you don't really do enough to reconcile H0. So there's a couple of H0 values quoted down here, which are not really getting up above 70, never mind up to 73. And there's this additional problem that you exacerbate this S8 tension with some large-scale structure data. So you can see in this plot here, there's a ratio of the best fit early dark energy power spectrum, this is matter power spectrum, to the best fit lambda CDM case. And this excess on small physical scales is disfavored by data from weak lensing surveys and from data from BOSS going beyond the BAO and looking at using the full redshift space power spectrum. So I mentioned this model because I do think it's interesting. It's arguably a bit contrived. It's not really clear. You have to get this timing kind of right, otherwise you don't even get the CMB right, never mind these other observations. I think there's maybe some mileage in models like this still, and I know people are still working on it, but nothing sort of stood out as particularly compelling. And I wanted to, instead of talking about more theory models, I wanted to just kind of go through a bit of a thought experiment, I suppose, relating to this idea of changing physics in the early universe. And this is something that bothers me. So imagine, we're taking the data at face value, we play the game where H0 really is 73. But if we're not changing expansion at late times, let's only just focus on, changing physics in the early universe. We also know that the uncalibrated supernovae and BAO agree well on the late time expansion history. The combined constraint on the matter density is very close to 0.3. And this is independent from the CMB. And it's independent from how long the sound horizon, how long the actual ruler length is as well. This just comes from looking at the same ruler at different redshifts, right? Or from the supernovae. So let's play this game where we assume we need some new physics that takes us from the Planck plus BAO lambda CDM value to this point in parameter space, roughly 73 and 0.3. And my point here is that this point is actually very far from the lambda CDM solution. So here I've shown, 0.3, 73. And if you just had to go in H0, so just in the up direction here, you're looking at about 13 times the lambda CDM uncertainty from the Planck plus BAO constraint. In 2D, it's even further away from the lambda CDM solution, because you're not really going along the long direction of this error contour. So the estimate I came up with was more like 65 times lambda CDM uncertainty. And that's not a problem, right? Nobody's saying lambda CDM has to be correct or lambda CDM has to be almost correct. My point here is just that, lambda CDM is very far, really, from the true model in this scenario. And the thing that really bothers me about this is that it's then kind of some bizarre coincidence that the lambda CDM model then seems to actually fit so well. So, just illustrating this, from before WMAP to after WMAP, the lambda CDM parameter space shrunk by a few times 10 to the 4. Planck added another factor of a few hundred. So that's a huge reduction in volume, at which point some problem with the model could have been found, but wasn't. And of course, there's other data supporting lambda CDM2 that I've kind of touched on. So the consistent message from the data sensitive to the early universe is that lambda CDM is a good fit. And if you'd have to make a change, it would be some kind of perturbation rather than sort of the much larger change that this logic before was implying. So, I'm not trying to dissuade people from thinking about new theoretical ideas. I still think there's some mileage for exploring models in the early universe. I'm just bothered that, why does lambda CDM fit so well if that's where the problem is? Okay, and just to finish off in the last few minutes, talking a little about what we should do about this. So something I hear a lot is we need more data, and that's fine. But to me, I think we need to. There's a quality versus quantity kind of issue here. I think this whole attention business has illustrated the need for clear assumptions, passing, setting, internal consistency tests, redundancy in these different observational methods. How are confirmation bias, other biases, optional stopping problems going to be avoided? I mean, this is a huge issue for surveys, and a lot of people are taking this very seriously. Also reproducibility, public data, and also code. And I want to just shout out a collaboration I'm part of, the ACT CMB collaboration for trying to move in this direction, do more than just release the data, actually release code so people can work with it, reproduce the results more easily. And there's a couple of links here if you're interested in that. Just very quickly, a couple of last things that I personally have worked on recently, trying to shed some light on the tensions. So I talked about this AL physical sort of changing lensing, and I worked with grad student Josh Cable on extending this idea to other physical effects, sort of deconstructing the power spectrum. So we invented new parameters that turned up or down the Sachs-Wolf effect, the Doppler effect, the early integrated Sachs-Wolf effect, these contributions in the temperature power spectrum. And then we threw them at Planck basically as extra fitting parameters, and trying to see if, do we get any extra clue here as to what's happening. And the main thing I learned from this exercise is just how constraining the Planck data are. So for example, we can fit, the Sachs-Wolf amplitude as an extra parameter here, as well as all the lambda CDM parameters at the same time, and get a 1% constraint on the Sachs-Wolf amplitude. So we didn't really end up learning, no new clue really about the AL puzzle. But this was still a pretty interesting exercise, I think. And just lastly, recently there've been this paper from the SPT team pointing out that there's this trend of high H0 values inferred from the E-mode polarization data, these gold points, across these different surveys. And so I looked at this and thought, is there any chance this is some clue relating to the Hubble tension? Is it possible that there's a problem in the model that's a bit different in temperature and polarization that manifests itself in this way? And so I looked into this, and indeed, when you take these measurements individually, you get these higher values, so 70, 72, 73. But when you combine these three surveys together, and they're actually close to independent because the E-mode data is noisy, so we don't have to worry too much about overlap of cosmic variance here. You end up getting drawn to a lower value that's in some mild tension with the distance ladder again. And I wrote a paper trying to understand this. And basically what's happening is you've got a six-dimensional parameter space, H0's just one parameter, and the parts of parameter space that are acceptable to all three of the data sets end up being on the low H0 side. And I've tried to illustrate this here. So the combined fit is in blue, then SPT, ACT, and Planck individually are in red, green, and gray. And if I actually go to the next slide and zoom in on some of these panels, looking at these parameter constraints, this is all lambda CDM, for NS against H0, these dashed lines with NS of 0.99, H0 of 73, they're all allowed within 1 sigma of the individual experiments, but the combined fit then ends up being almost 3 sigma away from that point. And it's because of these changes in degeneracy direction from the different experiments in other pairs of parameters. So I showed here, one including the baryon density. But it turns out that this is completely expected just from the ranges of multipoles that the experiments are sensitive to. And you can reproduce this behavior of these different degeneracy directions in the temperature power spectrum too, and in Fisher forecasts. So, my final conclusion from this analysis is that actually there's no real indication here that there's anything funny going on. It's a bit of a coincidence that the 3 experiments individually prefer higher H0s, but it also isn't so surprising that when you add them together, you get pulled back towards a lower value. So perhaps not the interesting clue I was maybe looking for there on the Hubble tension side. Okay, I want to wrap up. I'm sorry for going a little late here. These are my conclusions. I think this remains a very interesting problem. I didn't want to be, sound too down on theoretical developments and directions. I do still think the space for interesting theoretical developments here. I think it'd be great in particular to rule out broader classes of models. That's something I don't feel like has been done in the way it possibly could. But of course, one has to remember how constraining the data are. This is another challenge too. You don't want to be writing papers that are missing out, forgetting about key data sets. Okay, that's all I had to say. Thanks very much, and I'll take questions.
Excellent. That